In this video, I will show you about the how to derive ordinary differential equation of a simple system. The system consists of resistance component and capacitor components. Firstly, we determine or identify the variables and also the parameters and also the input and also the output. Firstly, the input. In the system, the input we determine as voltage input voltage. The output in the system we determine the output. For the system also, we need to determine or identify the parameters. The parameter is resistive components and also capacitive components. For the resistive components, we can identify the equation will be Ohm law. This is the equation. For the capacitive component, we can have this equation. Then the governing equations. In here we have Kirchhoff. Or in other words, we have this equation that total is zero, the total voltage, or in other words, minus resistance voltage in resistance component and increased by resistance voltage in capacitive component equal to zero. Or if we want to manipulate the sequence, so we have a familiar formulation here. And because the Kirchhoff law, we also know that I is equal to electrical current in resistive components and also electrical current in capacitive components. Okay, next one. Then we have 1, 2, 3, and maybe 1, 2, 3 equations. Then let's do this one. After we have several equations, equation 3, we can explore or substitute equation 1, equation 2 to equation 3. So let's write down again, equal to VR plus EC. Then the VR, we will input the equation 1, right? This one is IR plus EC, we can include so we have this equation. Then we can transform the equation to Laplace. to plus. You need to assume that the initial condition is 0. The initial condition of what? O is 0. Then we can make a Laplace transformation. Then we will in this equation, all is time as a function of time. After we have Laplace transformation, we'll have in frequency domain. It is integral, right? So we have 1s. So because we already transform to Laplace, we can take out the I r plus 1 per c s. Unfortunately, in this equation we already determined that the output is way out. Okay, so we need to convert all the variables, this variable and this variable, to these two variables. We in already here, and then the I, we need to convert I to V out. How we convert it? Let's use the equation to convert it, transform it to Laplace. Then we have here. Then we can manipulate the equation to be BCCS. Let's call it the fourth equation. This one is the fifth equation. Then let's combine equation 5 and 4. Yeah. Then we will have BCCS R plus 1 CS. Let's correct it a bit. Then we will have Laplace transformation. BC output divided by the input. Then we'll have this equation here. R this is the transfer function. Okay, let's do it one more. So you need to remember, we need to determine the variable. What is the output? What is the input? The output is V out, right? The input is V in. Or we can say this, the V out is VC, the voltage in capacitor. Okay, we already determined the variables. Then we need to identify what is the parameter R C. Okay, we only have two parameters. Okay, we already have variable parameters. So let's analyze the system. Let's analyze based on the parameter first. Firstly, the R. What we have here, R is resistive components. So we have what we call it, Ohm law. Then in the capacitive component, we have this equation. If you remember, integral and then let's see about the Kirchhoff law. You can see here the total voltage will be 0, right? So we can say V in minus VR minus C is 0. Or we can manipulate the equation a bit. Okay, so let's say Kirchhoff law also the I is, or electrical current is the same because the series relation, yeah, right? Or this one is equal I R equal to IC. So we have 1, 2, 3. So we have 3 equations. So based on the equation, we can say R plus C, and we need to remember that the input is in, the output is out. From these variable definitions, we can expect that the transfer function will be V out divided by V in. So the transfer function is about the formation, or the structure will be always like this one. Output divided by the inputs, and then we have this one. The form will be like this one. So if you already determine the input is input voltage and the output is output voltage, the structure, the last form will be like this one. Okay. Okay. We need to remember that V out also equal to VC. Yeah, the capacitive. So in this equation, we already have V in and VC, all in time domain, yeah, or a function of time. If the voltage inputs drop, maybe VR or VC will also drop. This is a time domain, yeah. In this equation, we already have Vin as the input and Vz as the output. Then we only need to convert Vr to Vz. Okay, let's input the Ohm law equation to Vr. So we have Vr plus C. Okay. Using the second the capacitive equation, we also know that the Vc is integral because IR is equal to IC. Now we can say that we only convert this one to be IR is IC, where IC is then we can input this equation to the equation. Then we will have C dVc dt R plus C, like this one. Then we can have a Laplace transformation. We'll have this one. This one is a function of S, S is a Laplace operator. Then we will have transfer function here. So we only need to bring this equation here. We can firstly take out the Vc. Then we manipulate the form, the equation, to be like this one. So this one is the transfer function.